Good afternoon or good morning, depending on where you are. My name is Professor Duke Orata. We are continuing with our lectures. And we are going to look at eutectic mixtures. Now, these eutectic mixtures, we are going to look at them in light of simple eutectic diagrams. So what does that mean? We are going to see what happens when you have freezing curves. Freezing curves, that means you mix components, mix some two components, heat them, form an homogeneous solution at high temperature, then cool them bit a bit to generate the freezing curves. When you generate the freezing curves, that is the curves which will tell you at what temperature for the various mixtures will you get solidification. Those are called freezing curves. So in this particular case, you have freezing curves. So you have temperature and you have composition. So you have component A and B. And each of them has a freezing curve. They have freezing curves. So like for example, when you mix 10%, a mixture which has 10% A, 90% B, you heat it up, you get a homogeneous solution, then cool it and see where the crystallization starts. Again, mix another set of mixtures, maybe 40% of A, 60% of B. Repeat the same process, do that for 80%, 20%, and then you will have the freezing curves. So when you have the freezing curves, you're going to see that these freezing curves intersect at this particular point, which corresponds, that's the eutectic point, call it eutectic point, and that can be considered as the eutectic temperature. Let's call it eutectic temperature, EU. Let's call it eutectic point temperature. This is a freezing curve, or what we call a liquid curve. So here we have liquid. Here we have component A, component B. The mole fraction of B is increasing in that direction. The mole fraction of A is increasing in this direction. In other words, here you have 100% A. Here you have 100% B. Here we have the liquid phase. So what happens? These are freezing curves. So that's the liquid. L is the liquid phase. So what happens with these systems? Now, if you take a state point, you have a state point. Let's call that state point A. State point A. No, let's call it C, because you already have A and B. Let's call that state point C. What is a state point? It's defined by some thermodynamic variables. So let's call it C. In other words, you can read the composition. The composition here is 100% B, so maybe it's 80% B and 20% A. Now, when you lower its temperature along this line of constant composition here is referred to as an isopleth. It's referred to as an isopleth. You lower the temperature along this line here, along this line of constant composition. So as you continue here, you are still in the region of the liquid region where you have the homogeneous liquid phase. Now, when you reach the freezing curve here, or the liquid curve here, let us call that point D, state point D. At state point D, you will have the first crystals of B crystallizing out. You'll have the first crystals of B crystallizing out in this region here. You'll have the first crystals of B crystallizing out. So we'll have liquid plus B. Liquid plus B. And the composition of the liquid is given by this point. Let us call this E. Let's call that small e. The composition of that liquid is given by that state point E prime on the liquid curve. And as you continue, so we'll have crystallization at point E. So at point E, state point E, we'll have D will have crystallization, formation of D. And of course, as you continue down the line, you are forming more and more of B. Crystallization of B. You're forming more and more of B. And we have said that the relative amounts of liquid and B can be got in terms of from Lever's rule. You get from the length of the segments. This segment here, this segment Y prime represents B, and that segment Y double prime represents this liquid of that particular composition. So you can determine that from Lever rule. We have discussed Lever rule or Lever principle in one of the lectures. So you can go through that particular lecture. So when we reach this particular point, when we reach this point here, that state point there, we have three phases coexisting in equilibrium. And remember, as you continue lowering the temperature, we are forming more and more B, and also we are saturating the solution now with A. So that when we reach this particular point here now, let's call it F. At that state point F, we now have we have component B and A coexisting together in equilibrium at this eutectic temperature. They are coexisting together in equilibrium with the eutectic mixture here, whose composition, let's say, is XE. So at that state point F, we have the eutectic mixture coexisting in equilibrium with component A and component B. Note, at the eutectic temperature, don't forget we have denoted it as TEU, eutectic temperature. We are having solids, we are having eutectic mixture XEU coexisting in equilibrium with solids A and B. And what does that mean? In other words, we have three phases coexisting in equilibrium. So if you look at our discussions on phase equilibria, we said that because these things are done under constant pressure, so phase rule, which is normally C minus P plus 2, remember C is the number of components, P is the number of phases, and these two stand for pressure and temperature. So we are saying that under constant temperature, under constant pressure, the phase rule under constant pressure, which I can denote with the subscript Fp, will be C minus P plus 1. Remove that because now pressure is constant. So we are left with only one variable there. So here we have three phases coexisting in equilibrium. So the variance of this system, or the number of degrees of freedom which you have at this particular point, is you have two components and the three phases A, B, and the eutectic mixture. That is three phases plus 1. And so what we have here is 0. So the system is invariant at that point. Invariant. Therefore, the temperature will be constant at that particular point for some time. And so finally, at some point, then you'll have lost sufficient heat, and so we will now continue moving down in that direction. And at this particular point where we are now having G, what we are doing is basically all the liquid. The liquid now is not there, everything is crystallized. So we only have A and B in this quadrant here. This section here now, so what you're doing here from F, as the temperature peaks and starts lowering now, you are merely cooling the solids A and B. So at G quadrant there, merely cooling solids A and B. Now, this is a simple eutectic diagram, and in practice, this is very common. These are very, very common in materials. Very, very common in materials. we can take an example of a real simple eutectic diagram. We have antimony and lead. This is lead, this is antimony. Of course, the mole fraction of lead, antimony is in that direction, 100%. Lead is in the other direction, 100%. And so, for the antimony lead system, because for pure antimony is 631 degrees centigrade, and the eutectic temperature is as 246. And for the pure lead, it's about 327 in terms of temperatures. So again, we have liquid at that particular point. Remember, if you take a state point there, so we just quickly run through it. Take a state point there and you are cooling it down. You'll have the first crystals of antimony forming, and you have the liquid. Antimony will be forming and you have liquid. So at that particular point, that is the composition of the liquid. Let's call it E prime, and we have the antimony. So here we have the antimony coexisting in equilibrium with the liquid. As you continue lowering the temperature, we reach that point where you have the eutectic mixture. Let's call it EU, eutectic mixture with the composition eutectic. At that particular point, the antimony is coexisting in equilibrium with the eutectic mixture and with the lead. So like we have said, the system is invariant. There's no change in temperature, as you have seen from the phase rule. And of course, at this particular point now, when the temperature starts lowering in this particular region now, as we start lowering the temperature here, we are now having formation of antimony. We have antimony and lead in this quadrant. In other words, all the liquid now is gone, so we now have antimony and lead. So we're just cooling antimony and lead. That's a real system. That's a real system, and there are many real systems as had many elements in the periodic table. So we can just summarize here and say that one, simple eutectic diagrams, we have developed them by simply generating the freezing curves, and you'll find the intersection of the freezing curves correspond to the eutectic point. And we have seen now that if you take any state point, for example, other than choosing the eutectic point, which we are going to see in thermal analysis, what are the characteristics of that particular feature there, you will see that you will have crystallization, and as you continue on, you'll have the liquid phase disappear completely, and now you have only the two solids which are cooling. And remember, in the two-phase region, we can use the lever principle to tell the relative amounts of those particular components. Thank you.